Hey guys, I'm here to help you with your Math 221 packet. This first video here is for the theory questions. Before I get going, I want to let you know that there is an online textbook that you guys have access to. It is right here. It's the BYUI Stats link. There's going to be a link for it in your packets as well. To get started, number 1 says, what are the 5 steps of the statistical decision of the statistical process? And so the first one is design the study. Number 2 is collect data. Collect the data. Number 3 is describe data. Number 4 is make inferences. And take action. Something that you would help the students with on these questions is matching them for different pieces of steps in the decision process. So if someone says, oh, Johnny went and sampled all of his classmates, or Sally made a histogram describing her findings, or Susie wanted to decrease the number of power motorboats so that she could save the whales, or something like that, then that would be some examples of questions that you would be working with. All right, number 2, what is the difference between an observational study and an experiment? By definition, in the textbook, an observational, a designed experiment is one where researchers control the conditions of the study. Usually that means that there's a control group and then there's an experiment group where there's the subjects being changed, where the conditions are changed. And then an observational study is where you have no control. No control. You're just walking around and you're just looking at what's going on. You have no control over anything else. Number 3, what's the difference between a quantitative variable and a categorical variable? So a quantitative variable is one where it's a number, and it makes sense to do math on it. Like adding, subtracting, multiplying, and dividing. For example, a lot of quantitative variables are measured. So, for example, how much money you have, how much you weigh, how high you can jump, how tall you are, how fast it takes for you to run a mile, and things like that. And so it would make sense to take my average running speed and your average running speed and divide it by 2 and take the average for it. However, a categorical variable is one where it's a category, or things like your favorite color, your brand of car you drive, if you smoke or not. And so these are mainly yes/no questions. Is your favorite color blue? Yes or no? Do you drive a Honda? Yes or no? Do you smoke? Yes or no? And so you would put people in various categories if they answer yes or no to this type of question. Some tricky ones where it's where it looks like a number and it's actually a categorical variable. I'll have some examples over here on the side. Tricky numbers. So these are actually categorical. Is a phone number and a social security number or any form of ID is actually referring to a person, because it doesn't make sense to take my phone number and add it to your phone number. It doesn't have meaning to it. It doesn't give you some sort of numerical value that makes sense. And so they refer to a person And so that is why it is a categorical variable. These particular ones, they're tricky because they're numbers, but they're categorical variables because they refer to a person. All right. Number 4, list each of the sampling methods and their defining characteristics, like what sets them apart from the other things. All right. The first one is a simple random sample. This one's the best one that you can get and is highly recommended. It's a random selection taken from a population. Selection from a population. Number 2, a systematic sample. A systematic sample has a random starting point. And we do every kth item. And so, for example, if you're looking through cereal boxes and you want to grab every 6th item, K is 6. And so this number changes depending on what type of study you're doing or depending how you're going to sample it. The third example of a sampling method is going to be a cluster sampler. Cluster sample. And that is where you take all items in one or more random clusters or blocks. All items in one or more random clusters or blocks. And so by that, I mean, if you have lots of different categories that are pretty similar to each other, you would take all of the first block. And for the purposes of that experiment and the way that you're gathering your data, it would be an accurate representation of the whole population. Okay. Number 4 is going to be a stratified sample. Stratified sample. And this is a simple random sample from every group. And so all of the GOUP. And so this takes all of your different samples and takes a few from the first one, and a few from the second one, and a few from the third one, and a few from the fourth one. And so because all of the data are in similar groups but have various defining characteristics, you would take a simple random sample from every group, from every strata. Cool. The last one is a convenience sample. A convenience sample. It is a less than systematic way of gathering your data, and you should avoid it at all costs. It is not good to use a convenience sample to gather your data. All right, moving on. Number 5 asks, what is a null hypothesis? Now, lesson 2 doesn't go into a ton of detail about null and alternative hypotheses, but it's good to have a good background and definition of it. And so the textbook says the null hypothesis, we signify it with a capital H and a subscript of an O or 0, is the foundational assumption. The foundational assumption about a population. And then this is the main part, it's the status quo. An alternative hypothesis, we usually denote it with an H and a lowercase a, is a different assumption. A different assumption about a group, about a population. Awesome. Number 7. So there are lots of different distributions that you may have learned in your previous statistics classes, but these 4 are the only main ones that we focus on in this class. Okay. A bell-shaped curve is going to look something like this. Right? It has a curve at the top and has a smaller distribution at the bottom. And then a left skewed and right skewed can get easily mixed up, but remember that the right skewed has, the left skewed has a lot of, or it has few in the left tail. It's just a speech. Let's see here. It looks something like this. And then the right skewed has a lot in the left and a few in the right tail. And so it's easier to remember the left skew has a few in the left tail and the right skewed has a little bit in the right tail. And then uniform is exactly what it sounds like. It's gonna be pretty straight, it's gonna be pretty boring, pretty normal, but that comes from like random number generators and stuff like that. Awesome, fill in the blanks. So from lesson 3, we learned population parameter and sample statistic. And the reason why this is important to know is because they're going to give you various homework assignments are going to give you or the students questions like which number describes the population, and so which label the parameter or label the statistic. And so we can use alliteration here and notice that a parameter starting with the letter P describes the population, and a statistic starting with the letter S describes the sample, a smaller group within the population. Awesome. Number 9, draw a box plot and label the associating numbers of a 5-number summary. All right, a box plot, some people call it a cat and whisker plot, but it looks something along the lines of this. The first number in a box plot, or the leftmost in the first number in a 5-number summary, or the leftmost in a box plot is the minimum. The next one is a first quartile. We've got the median, not the mean, the median, the third quartile. And then over here is the maximum. All right, if you don't remember what a first quartile or a third quartile is, first quartile is the 25th percentile. And the third quartile is the 75th percentile. Think of it kind of like money, like 3/4 is 75 cents, or 1/4 is like 25 cents. We'll define percentiles a little bit more in the next page or in the, later on in the assignment. Awesome. Number 10 goes through the 3 rules of probability. Now, you may have done like flipping coins or rolling dice or anything in your previous class, but this gives context to what a p-value is, of what probability is. So the 3 rules is that a probability of an event happening has to be between 0 and 1. It's be between 0 and 1. The second one is if you list all the outcomes of something happening, the sum of the probability of all of the events is 1. They all, when you add them all up, it adds up to 1. And then the last one is the probability of something not happening is the same thing as 1 minus the probability of it actually happening. Awesome. Moving on, number 11 asks you to fill in the normal probability curve with the right labels according to the 68, 95, 99.7 rule. Awesome. And so the 68, 95, 99.7 rule says that between -1 and +1 standard deviations away is 68% of the data. And then 95% of the data is between -2 and +2 standard deviations away. And then between -3 and +3 is 99.7% of the data for a normal distribution. Awesome. When do you use the 68, 95, 99.7 rule? Only when instructed to do so. So there's some of the times when you're going to use a normal probability applet, and there's some of the times when you're going to use this rule. This is an approximation. approximation. And so it's not going to give you exact numbers. And so only use this rule when instructed to do so. Number 13 asks you to write down the z-score formula used in this class and label each variable. Okay, so the one in lesson 5 is z equals x minus mu over sigma. I'm going to label these. Z, x, mu, and sigma. So we speak this, sigma. It's a Greek letter. Greek letters are really hard for these 221 students to understand, so be patient with them and use those words over and over again when you're describing these things. All right, sigma is the number of, it's a standard deviation. Sorry, let's see here. It's a standard deviation and it describes the spread outness of data. Standard deviation, spread outness of some data. Mu is the population mean. We speak it mu. Kind of like what Kat says, but it's spelled mu. And so that is, if you add all of the people in the population and you divide by how many you have for a quantitative piece of data, this is what you're going to get, the mean. That's usually given to you. And then X is a single sample, or one piece of data that you're comparing to. And then Z, a z-score represents the number of standard deviations you are from the mean. You are away from the mean. Awesome. All of these go to number 13. Sweet. Okay. What should QQ plot look like if it's normally distributed? In this class, when we're trying to determine if data is normally distributed, we like to put it in a QQ plot, something that Excel does for us. And so it should look like a straight line. Yeah, it'll look like a straight line. And then it looks something like this. It'll be up and to the right. In this class, we'll look on later in terms of diagnosing QQ plots and when it's normal and when it's not. But it's a little bit of an art where you squint your eyes, you tilt your head, and you're like, yeah, that's normal. Awesome. What is a percentile in lesson 5 or 6? So a percentile, let's see here, is defined by, let me get the actual definition real quick. A percentile is a number that represents a spot in the data. A spot in the data, usually someone's particular measurement, that is greater than or equal to some percent. It's easier to do it in an example. So for an example, if you are in the 70th percentile, that means that your measurement is greater than or equal to 70% of the data. Or that you're the same as or less than 30% of the data. Sometimes they'll use this in other interpretations for various homophonies, but don't dwell on that one too much. Okay. Number 16, what is the mean of the distribution of sample means? Now you might be like, what does that mean? Like you're just using two words here. Okay, so what's going on is if we have a population, and in that population we take a sample. Take a sample with sample size n. And within that sample, we could have an average. And within that sample, we can also have a standard deviation. We can have spread outness within that sample. And so what this question is asking is, what is the mean of the distribution of sample means? What is the average of how this sample is distributed? And so the numerical value to represent this is mu, which is the same thing as the population. This next question, number 17, before I move on to the next slide, it asks what the standard deviation of the distribution of sample means. It asks if you have a particular sample size, it has its own spread outness. A whole population has its own mu, and it has its own sigma, it has its own spread outness and its average, but each sample can also have that. If you grab a small sample, you can find an average. If you grab a small sample, you can get a standard deviation, which is S. So the numerical value for that is sigma divided by the square root of n. Okay. It's going to be a little bit difficult. And so I'd like to draw a chart for the students who are taking 221 and say, if we have the parent population here and the distribution of sample means, which means how the sample is distributed. And then we have a category over here that means is the mean, and over here that's a standard deviation. The mean for the parent population is mu. And the mean and the standard deviation for the parent population is just sigma. We all know that. That's just the symbols that we use to represent it. The mean for the distribution of sample means is also mu, like what I just said from number 16. And the standard deviation of the distribution of sample means is sigma divided by the square root of n for this class. Awesome. We're almost there. Define the central limit theorem. The central limit theorem says the distribution of sample means is normal. Is normal when x bar is normally distributed, or when n is sufficiently large. Sufficiently large. And for the purposes of this class, sufficiently large means just n is greater than or equal to 30. But for other classes, it might be not enough. Or when n is sufficiently large. N is greater than 30. Awesome. Defining the law of large numbers states that as the sample size, or n, gets larger, x bar, which is the sample mean, gets closer to the population mean, which is mu. And this makes sense, right? So if we have the entire state of Idaho, oh look, there's Idaho, and we were to sample just Madison County, would that be representative of the whole population? Probably not. But if we were to get Madison County and Bonneville County, that would be a little bit better. If we were to do Madison, Bonneville, and another nearby county, it'd be better. And so as we add more and more people to our sample, it would be more representative of the whole population of the state of Idaho. And so as we sample more people, as the sample size gets larger, the sample mean, as the sample size gets larger, the sample mean, which is x bar, gets closer to the population mean. It more accurately represents what we're trying to measure. Awesome. Okay, the last one, it says number 20, write down the updated z-score formula used in lesson 7. When should you use each one? Okay, so the new z-score formula is z equals x bar minus mu over sigma divided by the square root of n. So this one uses X bar, and I'm going to write this down, X bar, which is the sample mean for a particular set of data. And notice that it has an n, which is a sample size. It uses a new number. And so this takes our new concepts that we just learned from number 16 and 17 of using a sample and using the, and its mean and its standard deviation and calculating a z-score. When should you use each one? We should use the first one when only given one sample. One sample. We could use the second one, this new one, when given a sample size. Which is pretty much when you're given n, you use the new one. You use the one that has an n in it. Awesome. Thanks. We'll see you in the next video.